So we have a spring attached to a ceiling, pulled down 15 centimeters from equilibrium, and then released. The amplitude decreases by 20% each second. The spring oscillates 8 times each second. Find an equation for the distance. D, the end of the spring, is below equilibrium in terms of seconds t. So spring hanging down, and it's got this equilibrium here. And then we pull it down 15 centimeters, and we're measuring how far it is below its equilibrium, so down is positive. So this is the 15, it's going to be the furthest it's going to be away, right? So that's going to be the max right there from the equilibrium, which is its average, right? Midline, equilibrium. So since we're starting off with it being at its max, we're going to want to use a cosine function here. And then the 15 centimeters is going to be my amplitude. Now it oscillates 8 times per second. So they're telling me the frequency, because remember, frequency is a per second. So they're telling me the frequency is 8. The frequency, remember, is the reciprocal of the period. So the period is 1/8. So if it oscillates 8 times in a second, it makes one oscillation in 1/8 of a second. So that's my period. Consider our 2 pi over b, multiply the b up and the 8 up, and we get b equals 2 pi times 8, or 16 pi is going to be our multiplier there. Now the amplitude isn't constant because they're saying the amplitude decreases there. So my amplitude is this decreased by a percentage amount right here. It starts at 15 though. So that's going to give me an exponential function, 15 times 1 minus that percentage as a decimal to the power t, right, each second. Clean that up and I get 15 times 0.8 t. So that's my amplitude right there. And we're just oscillating around the midline, so we're just going to call the midline y equals 0. So we don't have to add anything to this. So putting that together, we've got our amplitude, 15 times 0.8 to the power t. And then we have a cosine because we're starting at the max. Our multiple for this frequency and period is 16 pi times t. And we don't need a phase shift again because we're starting with cosine at the max, and we're not adding or subtracting anything outside because we're considering equilibrium to be a 0, and we pulled 15 from that. That should be it. Let's take a look at the graph. So what we should see, again, this is a damped wave. We should see that the amplitude is shrinking as we move along. And let's refresh Desmos. All right, so I'm going to call this D for displacement. We're going to use X instead of T. And we think it is 15 times 0.8 raised to the X. So that's that dampening part times this oscillation, cosine of 16 pi X. Whoa, it's oscillating very fast in this window. Let's see, what is my window? Negative, we don't need those negatives. So let's go X over here. Let's start off at 0. And remember, it's oscillating 8 times per second. And I'm looking at 10 seconds. So that's going to show 80 oscillations. That's kind of a lot. So let's maybe go for 3 seconds. That'll be 24 oscillations. Oops, not 13, I want 3. And then remember, it has a max pull of 15. So maybe if we go like negative 20 to 20, we should, oops, not 720, 20. Yeah, so here we can see that damped oscillation. So it's oscillating 8 times per second. Is that true? Here's 1 second. I have 1, 2, 3, 4, 5, 6, 7, 8 oscillations in that 1 second. So there's my frequency. And that is dropping by 20% per second. And so that's just going to keep slowing down and slowing down until we hardly see it moving way out there. And that doesn't really simplify any further. It doesn't simplify any further. So 15, 0.8 raised to the, they want a t here, times the cosine of 16 pi t.